All right, our third lesson in chapter 2 is about the product rule. So yesterday we saw that when you have a sum or an addition of two functions, you can just take the derivative separately. It doesn't work that way for the product rule. So first we're going to talk about what it's not. I'm going to show you why that doesn't work. So let's say I have two functions. F at x is this line and g at x is this parabola. Well, I can take the derivative of each of those things separately. So for f prime at x, just taking the derivative of this line, the derivative of 2x would be 2. And then I get x to the 0, which is just 1. And then the derivative of 5 would be 0, so I'd have plus 0. So I'll just end up with 2. Then taking the derivative of g at x, taking the derivative of the first part, I get 2. I bring the exponent down, and then x to the power of 1. And then it's an addition, so I just take this derivative separately. Taking the derivative of 3x, I just take the exponent 1, bring it down and multiply it with the 3. And then I would have x to the power of 0, which is just equal to 1, and so I don't need to write that. So here are my two derivatives of the two separate pieces. So now what I want to investigate is what happens if I have a product of these two functions. So remember, product, that's the answer of a multiplication. So we are talking about multiplication when we talk about the product rule. So p at x, if I make it the product of the two, then it would be 2x plus 5 times the parabola up here. And it's asking us here to expand. So I can just, I'm going to FOIL it out, so 2x times both things in the second bracket. And then the positive 5 times both things in the second bracket. And then we'll collect those two middle terms. And now if I look at p at x as this last equation, then I have the sum of three separate equations, and I know that I can use the sum rule from yesterday to find the derivative. I can just take the derivative of those three separate pieces. So p prime at x then would be the derivative of 2x cubed. So I take the cubed down and multiply it by the 2. That gives me 6. And then I'll just subtract 1 from the exponent. And then for the second piece here, I've got 11x squared. I'm going to bring the 2 down and multiply it by the 11. And then I'll subtract 1 from the exponent. And then for the last one here, again, we've got an exponent of 1 here. I'm going to bring it down, multiply it by the 15. And then I'm going to be left with x to the power of 0, which is just the same as multiplying by 1. So I'm done there. So I know that this is what the derivative is. I know that this is true and correct. Now, the thing that people want to do when they start with a function that looks like this is they think that they could just take the derivative of the first piece and take the derivative of the second piece. So their guess is that p prime of x is equal to the derivative of the first piece. Remember, we said that was 2 times the derivative of the second piece. Remember, we said that was 2x plus 3. But we know that the derivative is actually this over here. And when I look at this, I can expand this out. It would be 4x plus 6. So the question here is, does p prime at x equal this? And no, I can see that it's not. This came out as a line, and this came out as a parabola. So definitely, this is not true. I cannot just take the derivative of each of the brackets. So sometimes you'll be able to expand out like we did here. But for a lot of functions, you won't be able to do that. So imagine if you had like a trigonometric function. Maybe you had like sine of x here, and you had a log function over here. Well, there's no way for me to expand that out. So I have to come up with a rule for multiplication that'll work without expansion. So expansion will work if they're both polynomials, but that's a pretty special case. So we're going to use first principles to find the derivative for the function p at x. I'm actually going to move that right over to the side because it's going to get pretty wide. So p prime at x is going to be equal to the limit of the difference quotient. So it's going to be p at x plus h minus p at x all over h. All right, so we're going to plug x plus h in for all three of these x's. So I'm just expanding the 2. I'm doing 2 times the whole bracket. So I've expanded that through. And then I'm going to do I'm going to do x plus h squared. And then 3 times x plus h will be 3x plus 3h. Okay, so that's p at x plus h. Now we need to subtract the original function. Okay, so I am going to do some more interesting algebra here because I'm trying to simplify this down to something. So what I notice over here is that I have a 2x plus 5, and I almost have that in this bracket here. So what I'm going to do is group the 2x and the 5 at the start of this bracket. So I'm going to say that this is 2x plus 5 plus 2h. And then over here, I'm going to expand this out, and I'm going to try to actually replicate the second bracket over here, the x squared plus 3x. I do not expect you guys to do this kind of work. This is part of my proof. And so it's just understanding where the product rule comes from. We are going to do a bit of fancy algebra when we're simplifying. It's not really that fancy. It's just going to look a little bit more complicated, but it's just common factoring really. And that's what I'm using here, but here I have to do some funny expansion to get that common factor. So now in the first bracket, I've got the 2x plus 5 factor from over here, plus 2h. And in the second bracket, I can see here the x squared plus 3x. I've got that. I've got an x squared here and a 3x here. So I'm going to pull them together at the front of the bracket. Oops. And then I'm just going to write the leftovers in another inner bracket here. So it'd be like h, oh, there's actually an x, so I'll put that first. There's a 2hx. Plus h squared plus 3h. So those are the bits that I didn't use up. So remember, I grabbed these guys here and put them together. All right, so why did I do that? Well, what I'm going to do is expand out these two brackets. So what I have in the first bracket is I have 2 terms. And then in the second bracket, I have a different 2 terms. I've got x squared plus 3x, and then this bracket here. So I'm going to multiply these 2 things by these 2 things. So just like I would normally FOIL it out, I'm going to take the 2x plus 5 and multiply it by both of those second brackets. So I'm going to get 2x plus 5 times the first bracket. And then I'm going to do 2x plus 5 times the second bracket. It's looking really messy at this point. That's okay, it's going to get better. Now I'm going to take the 2h in the first bracket and I'm going to multiply it through the second bracket. Okay, that's just this first bit all expanded out, and I still have this extra guy here hanging out at the end. Okay, right away I can simplify a little bit because what I have over here is the 2x plus 5 times the original parabola, and over here I'm subtracting 2x plus 5 times the original parabola, so they're going to cancel away to 0. And it's a little bit simpler. Now, what I wish I could do is cancel away this h in the denominator. So looking at my 3 leftover bits, I'm looking at this as 3 separate pieces. I've got one piece here, one piece here, and one piece here. They're separated by addition signs. I notice that this guy has a common factor of h, this guy has a common factor of h. Now there is no h in front of this one. When I look at the first bracket, there's no common factor of h, but in the second bracket there is. So I'm going to pull out that common factor of h from that bracket. So I'm going to have h times 2x plus 5 times, and now for that bracket, the common factor of h has been removed. And then these other guys already had the h factored out, so I'll just copy them down. You could pull a second common factor of h out of this bracket, but it's not necessary. All right, so now when I have these 3 pieces, these 3 expressions, they each have a common factor of h. I'm going to pull it out front. And this was all so I could cancel this h here. Okay, I need brackets around that because it's an addition. All right, and now we can take the limit. We can actually plug in 0 for all of these h's. So no h's in the first bracket. In the second bracket, I'm left with just 2x plus 3. And then in the middle, there's no h's left at all. And here at the end, when I plug in h is 0 in the second bracket, I'm going to get 0 plus 0 plus 0, and so I'm going to get 2 plus 0. So that just goes away. Or sorry, 2 times 0, so that just goes away. So what I've got here is my answer for p at x. Now, we're going to have to kind of scroll back up, so hopefully you've got your whole sheet in front of you. And what I see here are 4 pieces, and I'm going to try to identify these 4 pieces. So I've got this guy, the 2, and then this last bracket. So hopefully when you scroll right up to the top of the page, you notice that f at x was equal to 2x plus 5. So what I have here is f at x. And again, right up at the top of the page, g at x is this guy right here at the end. Now, I've got these 2 middle pieces here that I need to identify. So if you scroll back up, the first thing that we did in part A was we found the derivative of f, and it was equal to 2. And then the derivative of g was 2x plus 3. So that's actually what we have down here. The 2x plus 3, that's the derivative of g. And the 2 is the derivative of f. And this, with the addition sign in front of it, is the pattern for the product rule. So whenever I have 2 things being multiplied, I leave the first thing alone and multiply it by the derivative of the second thing. And then I add the derivative of the first thing times the second thing. And because it's addition, you can switch the order of these 2 things. It's not going to work when we have a rule that involves subtraction, like in our next lesson, but it will work. So you'll find that normally we actually write this first and this second. We're going to see that in our summary on the next page. Again, you don't have to know how to do this. It was just to develop this rule. I'm going to stop the lesson here and we'll continue in a second part.